Good morning. This is Miss Billerbeck, and we're going to talk about 3.1, relations and functions. So a relation is a set of ordered pairs, and a function is a relation in which each input is assigned only one output. Now you might say, well, what does that mean? Well, let's think about a vending machine. So if you have a certain amount of change and you put the change or the dollar bill into the vending machine, and you push one of the buttons when you select what you would like to eat or drink, then you expect what you selected to come out at the bottom of the vending machine so you can have it. Now, a functional vending machine would have one output for every input, which is every button you push is the input, and the output is the actual food or drink, okay? So that's a functional machine. But let's say you push the button and you get something that you didn't select. So sometimes it gives you what you want, sometimes it doesn't. Well, that's not a functional vending machine anymore. So it's more of a relational vending machine because it has a relation between that button, but it changes its direction about what food it's going to actually release and give to you. Okay, so that's what the relation is. Okay, but a functional machine, you know what to expect when you push the button. Okay, so the domain is the button that you push for your input. So the domain of a function is the set of inputs. The range of a function is the food or drink that comes out of the vending machine. So the range of the function is the set of outputs. All right. So let's take a look at this one. So we want to identify the domain and range of each function. So we see we have the x, and if we recall, when we do a chart or a graph, the x is always the horizontal and the y is always the vertical. Okay, so that's because this is the independent axis. So this is the one where you put the change in and you're pushing, okay? And this one depends on what you push. So it's the dependent. So I'm just going to write depend, but it depends on this independent one. Okay, so when I put my input of 2 into the machine, I always get a 0 for an output. There's no other 2 up here giving me a different output. So the x values are the domain. Let me make a little room here. So here we have the domain over the range of values. This is also called the input over the output. Okay, it's also called the independent and the dependent value. Okay, so that's the domain and range of this function. And we could write it as coordinate pairs 2, 0, 3, 1, 4, 2, 5, 3, and 6, 4. Okay, so when we look at this, our dependent our domain is the top value because that's the x. So we have domain and the range, the y value, which depends on our input, is on the bottom. So we have input at the top and output below. So another way to write the domain and range without writing it as coordinates points is you could write the set of domain for this particular one is -3, -1, 1, 3, and 4. The range is 1, 3, -2, 2, and 6. So that's another way you could represent the domain and range for these two. All right, so let's take a look at domain of a function being continuous versus discrete. Okay, so the domain of the function is continuous when it includes all real numbers. The domain of a function is discrete when it consists of just whole numbers or integers. All right, so when we see a continuous line like this, we see that time is continuous. That's one thing we know. We can't just break time up, stop time. Just there's no gaps in time. So time is continuous. And volume of fluid usually is quite continuous. You can't really slice a fluid with a knife. It just refills where you've vacated the area. So that's also continuous. Discrete would be something like the number of scholars. We can't have a part of a scholar or a half a scholar, or a third of a scholar. We have to have one scholar or two scholars or three scholars or four scholars or even 0 scholars. Okay? So if we had 0 scholars, we wouldn't need any desks. But if we have one scholar, we need one desk. If we have 2 scholars, we need 2 desks, 3 scholars, 3 desks, 4 scholars, 4 desks. So that would be discrete, where we don't need half a desk or a third of a desk. We need 1 desk, 2 desks, 3 desks. So that's discrete data. All right, so let's take a look at this one. So we're going to analyze each situation and identify if the domain and range are continuous or discrete and why. So we have a pinball machine and it costs 50 cents a game. All right, can we put in 25 cents and the machine will start? No, the machine will not start unless we put 50 cents in. So if we were to graph the pinball machine, so let's say we had, let's say games played and money put in. So this axis is money. Okay, so we're going to do 50 cents, $1, $1.50, $2, and $2.50. Okay, we can go to $3. We might get a little addicted to the game. Okay, but if we don't put any money in, we're playing 0 games. So at that point, if we put 50 cents in, we play 1 game. If we put $1 in, we get to play 2 games. If we put in $1.50, that gives us 3 games. And if we put in $2, that gives us 4 games. And then finally, we get our 5th game if we put $2.50 in. Okay, so this would be discrete data, and our domain is discrete, and our range is discrete. Okay, and we have a limit too. We can't play negative games. So our data is going to be discrete data greater than 0. And it would be all, let's say, we would do all counting numbers. Would be the domain. Okay, but for this one, for the range, we would have, oh wait, the domain is not counting numbers. That's the range, because that's what we're playing our games. Okay, so our range is counting numbers. We don't have 0 games. Well, I suppose we could have 0 games. So let's change that from counting numbers to whole numbers, because whole numbers include positive integers and 0. So whole numbers would be the range. Okay, the domain would be, I think the best thing for the domain would be, it would be where we'd have 0, 0.5, 50, $1, 150, $2, and 250. So that would be our plotted domain right here. So it's going to be positive, but it's going to have to deal with the numbers. What do we input into that pinball machine? Okay, so let's take a look at a different situation. Okay, so we have a Subaru car travels 25 miles using 1 gallon of gas. Okay, so I'm going to reuse a board right here. So if we change this and we say, okay, so we have miles per gallon. So our input, we literally input gas. Okay, but I have a restriction on the gas. So let's see, how am I going to fit that? So let's do 4, 6, 8, 10, 12, wait, 4, whoops, I did this a little wrong. Okay, 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So this is going to be gallons of gas. Okay, so this other one is going to be miles. So that's our output when we're able to actually have the input. So if we know for 1 gallon we can go 25 miles, then 2 gallons, which this would be 2 gallons, I could go 50. Okay, so then that means this would be 100. Let's just split this up and make it easier. 200, 300, 400. Okay, so my restriction on a Subaru is I have a 16-gallon tank. That's all the Subaru will carry. Okay, it will carry 0, and I would be in a very sad way if it was at 0. I wouldn't go anywhere. So if we plotted this, we could go from 0 to here, and so we're going to have to stop here at 16. So let's go ahead and graph this and see how many miles the little Subaru can go when we hit 16. So we're going to put this little barrier here that says we cannot go any farther than that. And we know the slope is just going to be like this. Okay, so that makes complete sense too, because most modern cars have a range of 400 miles. Now you've learned something. Okay, so if you're going on the loneliest highway, Highway 50 through Nevada, you want to fill your tank up because it's about probably 350 miles to the next gas station. So you want to make sure that your tank is filled with 16 gallons. You're getting 25 miles per gallon because that would be the slope for this if you get 25 miles per 1 gallon. Okay, and this data would be continuous to 16 gallons. Okay, so if we were to write what this domain is, so the domain we can write in set notation would be x such that, that little thing means such that, and then we have 0 is less than or equal to x is less than or equal to 16 if the tank was full. So that would be the domain using inequalities. Or we could just say the domain is from 0 to 16 gallons if we didn't want to. Okay, so that's the domain. Now the range, looking at this, well, that's from 0 miles to 400. So the range, we wanted to be fancy and use set notation. It'd be y such that 0 is less than or equal to y is less than or equal to 400 miles. Okay, so this really should have gallons right here. So I'm going to abbreviate it, gallons. Okay, or we could say from 0 to 400 miles would be our range. And that literally is the range. the roaming range of the car is 400 miles. So there you have it. All right, so let's look at another way to look at functions. So if we're classifying relations and functions, so a function is one-to-one if no two elements, remember elements are little parts of a set, so no two elements of the domain map to the same element in the range. So this is called mapping. Okay, so for this particular one, I would have these would be my coordinates. So I'd have 3, 2, 5, 2 right here. I'd have 6, 3 would be my coordinate, and 9, 4. So that's how it would map. Okay, so this one here is mapping where we would see 3, 1. This one would be 5, 2. And we have 5, 3 and 6, 4. All right, so the problem is that remember a function, for every input, it only has one output. So here are my inputs, and 3 has only one output, 5 has only one output, even though they have the same output. If I push button 3, I'm going to get that. So that just means 2 of the buttons have something like spicy Cheetos or something like that. So button 3, button 5 have spicy Cheetos. Button 6 have Kit Kats, and button 9 has, let's go with gummy bears. Okay. So they all have, for every input, there is one output. So that's what makes it a function. Okay, this one, however, we have an input here of 3 to 1. So we know what we're getting when we put 3 in. But 5 can be 2 different things. So if we do an input of 5, we don't know if we're going to get a 2 or a 3. So it's kind of up in the air which one we're going to get. So that's not exactly functional to not know when you have an input what your output's going to be. Okay, and then 6 goes to 4 so that we can anticipate. So when we can't anticipate which output we're going to get for the input, that's a relation. All right, so on this one, we have is this a relation or a function? So again, we think about it. Okay, if we push button -2, we get 1 output. If we push button negative or +3, well, we could get 6 or 7. So that means I've got a relation right here. So this is a relation. And the fact that 4 is going to 8, that's no problem at all. Okay, on this one, I have a 2. If I push button 2, I know I'm getting a 0. If I push button 4, I know I'm getting a 0. If I push button 6, I know I'm getting 10. And if I push button 8, I know I'm getting 20. So this is a function. Okay, now we have to look at curves. So if I have an input, I can only have one output. So let's do the vertical line test with my fancy engineering one. And if I pass a vertical line over this, if it only hits that curve once as I pass the line across, it is a function. So that's called the vertical line test. So when I pass it over that, it only hits that curve once. So this is a function. So it passes the vertical line test. All right, so if I take this here and I pass it over the circle, which we know and love, is this going to be a relation or a function? Let's see. Oh, this is a fail on the vertical line test. See how it's hitting right here, and that gets even worse at the diameter, right here, and here it hits. Okay, and it just keeps hitting until we get to the tangent of the circle. You aren't going to learn tangent yet, but you might as well. Tangent's like if you're throwing rocks on the water and you want to skip them, it's just hitting the top of the surface and skipping. So that's a tangent. Okay, and this little segment of talking about a tangent is a tangent. There you go. All right, so this is a relation. Okay, so we have one more to do. All right, so now let's just think about this. Okay, so we have Lorenzo's planning a dance in the gym and he wants to charge $10 a scholar. So we need to identify the constraints on the domain. Okay, well, if we know the input is we have $10 per scholar. Okay, so the dance is for the scholars. So if we were to write that out, we would put the scholars down here to see how much money we would make. So this is the dollar one. So usually dollars is an output. Okay, so we could range it from 0, but then the gym does have a fire department capacity. Let's say that fire department capacity is at 300. So we can only have 300 scholars. Okay, so if we're charging $10 a scholar and we fill the gym with 300 people, then that means that we're going to make 10 times 300, so that's $3,000. Okay, but if I only have one scholar, I'm just going to make $10. Okay, and then if I have 500 scholars, that, whoops, no, 50 scholars. Sorry, we can't do 500 because that would exceed the fire department standards. So if I have 50 scholars, that would give me $500. So you can see that, well, it should be discrete and it should follow a line. So this one would be $500. Okay, so when we're planning the gym, we know that our scholar is the domain. So our domain is from X such that 0 is less than or equal to the number of scholars. Well, they're the whole numbers. I guess we can't use that notation because this is discrete. So let's go ahead and say it is whole numbers to 300 because of the fire department. Okay, so that's the domain. And then the range, we could say the range, I'll just squeeze it in right here. So the range would be whole numbers to 3. Well, it's going to be multiples of 10. Of 10 to 3,000. Okay, so that would be the range. So if we put that like this, so we organize it just a little bit, there we have it. So the domain D is whole numbers to 300. So we're going to 300. The range will go from 0 to 3,000. Okay, so now we have Lalit has a monthly closed budget of $50. She maps the amount she spends to the number of items she buys. Okay, so let's say she buys 5 items and 0 items. And actually, let's start with 0 items because that's highly possible. So she starts with 0 items and then she chooses 5 items and maybe 7 items. Okay, so we'll just do a couple months. So if she does just buy 0 items, that's $0. But let's say she buys 5 items, and let's say one's a very expensive built. Okay, she could actually max out at 50. But then if she decided, I want a little bit more this time for my money, I can buy 7 items for 50. Okay, is this a function or a relation? Well, let's see. So we're going to map it out. And we've got that. Actually, we only do that. So is this going to be a function or a relation? So for every 0, we know we have that. But we could buy 5 items and it could be something other than $50 if we didn't buy the expensive built. And let's say we bought t-shirts and some shorts and they were only $30. Okay, so let's say that happened. So I don't need to write 5 twice here, but I do see that I could do that. So now we have a problem. Okay, for this input, I have 2 outputs. It depends on what I buy. So is this a relation or function? So this happens to be for this input, I have 2 outputs. So this is a relation. Okay. Versus this one's a function. So we have a function right here. We're actually putting on a function. And it's a function. All right. So then our domain could be 0 to 50. Well, we could buy various items. Maybe we could buy something in bulk like funny monkeys. And So we have no idea, but they're real numbers. Okay, and then the range would be $0 to $50. Let me make that bigger so you can actually read that. So $0 to $50. So that would be the range for that. Okay. But the reason why I say all real numbers for the domain is you could buy thousands of funny monkeys probably for $50 if you found the right vendor, the right person to buy it from. So you just don't know how much you can buy for $50. All right. So that's it for this lesson. I hope you have a wonderful day. Bye-bye.